Hi guys, Miss Francis here, and I'm hoping to continue our discussion regarding diffusion and osmosis. Diffusion is the tendency of molecules of any substance to spread out in the available space. In other words, it's going to spread out in the direction of a high concentration to a low concentration. And this is a type of passive transport because it requires no additional energy, no ATP. Now, which molecule spreads out or which molecule crosses beyond the semi-permeable membrane is purely random, where that diffusion is driven by the intrinsic kinetic energy of molecules. So, for example, if I were to increase the temperature, I would increase the rate of diffusion because I'm increasing the kinetic energy. Take this situation where I've got molecules of dye on one side of a semi-permeable membrane. There's a high concentration on the left side and a low concentration of the dye on the right-hand side. So my dye is going to diffuse from the left to the right side of the semi-permeable barrier, semi-permeable membrane, where the net movement goes from high concentration into low concentration until I have equal concentrations of the dye on each side, and that's called dynamic equilibrium. Now, it doesn't mean that my dye has stopped moving. It just means that my dye is moving at an equal rate on either side of my semi-permeable membrane. So now let's talk about osmosis. Osmosis is also a type of passive transport because it requires no additional ATP. However, when we're talking about osmosis, we're talking about water crossing a selectively permeable membrane, where the water is going to move from an area of high concentration to low concentration. This McGraw-Hill animation is a really good animation that shows how animation works. If we were to compare and contrast diffusion and osmosis, they are both types of passive transport because neither requires added energy, added ATP. But like I said, osmosis involves water moving, and it occurs across a semi-permeable membrane. So if I were to fill out my notes, how would I describe a hypertonic solution? Well, I might say that a hypertonic solution is a solution where there is a high concentration, of solute, but I've got a low concentration of water. Now, let me give you this example. Let's say I've got a beaker that's got tap water. So it has some minerals, maybe fluoride in it, as compared to a beaker of distilled water. In this case, how would it compare? Well, in this case, because my tap water has more solute than water, it's considered hypertonic. So let's continue. Defining a hypotonic solution. Well, a hypotonic solution would have a low concentration of solute, but it's going to have a high concentration of water. So now let's take our example again. Let's take our beaker of tap water. That's got some, I don't know, fluoride in it. But now let's compare it to a beaker of ocean water. Now, ocean water is going to be full of salt. So in this situation, now our beaker of tap water is hypotonic, whereas before it was hypertonic. So do you see how these terms are comparative? They're all relative to the situation. And an isotonic solution is when you've got equal concentrations of solute relative to solvent on either side of the membrane. Now, when I have an isotonic solution, that doesn't mean, though, that my solute has stopped moving. It's just moving at an equal rate. Continuing on, if I were to predict what's going to happen over time with this U-tube, what would I predict? Well, first of all, I'm going to make note that my water is going to move from a hypotonic to a hypertonic solution. And I also want to make note that my solute is too big. So I just want to concentrate on the water. And would you take a look at what would happen over time? My water level on side B would raise, whereas my water level on side A would lower. However, when I look at the concentrations on side A relative to side B, I now have equal concentrations because side B was diluted by adding water to it, whereas side C had water removed from it, so it became more concentrated. There are also 5 additional vocabulary words that we can use to describe solutions or solutes that are in a hypotonic situation versus a hypertonic situation. So if I have a hypotonic solution, I know that I have a low solute concentration, so I've got a high water concentration. If I have a hypertonic solution, I have a high solute concentration, but a low water concentration, which is the same as saying I have low osmotic concentration in my hypotonic solution, and I have a high water concentration on that side. And we already said this, right? High water concentration. Now, please don't use the words lots of water or no stuff. Make sure you use key vocabulary words like solute and concentration. On the other hand, in our hypertonic solution, you've got a high osmotic concentration. You've got a high amount of solute, a high concentration of solute, where you've got a low water concentration, which we already said. Now, let's talk about water potential. When I'm talking about water potential, does my solution have the potential to lose water? Hypotonic solutions have a high likelihood of losing water, whereas hypertonic solutions have a low likelihood of losing water. Now, water potential is actually measurable. We can calculate water potential, which we will do in one of our labs. But let me show you this one thing. When I'm talking about water potential, the highest water potential I could have is 0, and that is found in distilled water. It's got the highest amount of water and the lowest amount of solute. As I go towards a larger negative number, the solution becomes more hypertonic. It has an increasing amount of solute, meaning I went from a high water potential to a low water potential. A high likelihood that I would take up water to a low likelihood of taking up water. And lastly, another vocabulary word that can be used to describe osmotic situations are low osmotic pressure refers to having a hypotonic solution, and high osmotic pressure refers to a hypertonic solution. In other words, the hypertonic solution is very likely to take up water, so it's going to have a lot of pressure because water is flowing in. So that's our discussion of diffusion and osmosis, and we'll build on this lecture as time goes on.